Okay, I hope the presentation is visible and I'm properly audible.
Yes, ma'am.
Okay. We will wait for 5 more minutes and then we'll start with today's session. Okay, I think we should start with today's session. So, uh, for the week 7, this is the week 7, as previous week we have not taken any classes. So, for the week 7, sir, like we'll go through first what sir taught in class, that is the Euler's equation and the Bernoulli's equation. So, how it was derived and all. So, just a brief detail of all that. So, first of all, we have studied the kinematics and now we are going to dynamics of inviscid flow. So, what are the forces that are acting here? So, first of all, there is surface forces and another is body force. So, we need to take both of them into consideration, and both of them will give rise to mass and mass into acceleration, that is the force. So, this we are considering in inviscid flow. Okay, so let's consider a 2D fluid element. Okay, so if we consider a 2D fluid element, let's suppose this is a 2D fluid element, and this is the pressure force that is applied on left side, that is P, like if this is 1, side 2, and this is delta x, and this is delta y, and this is the pressure force that is applied on this side. Okay, so this is delta y, right? So this what is the pressure, like force that is applied on this side because of the pressure of the fluid that is present on this side. This is P delta y multiplied by, if the thickness is like the thickness on this side, that is the z side, z axis is 1 unity, and on this side, because the fluid have traversed this length del x, that's why this will be P plus del P del x delta x delta y multiplied by 1. So consider like body force on this. What is the body force that will be applied? So the body force that is applied is density multiplied by body force, that is per unit mass, and delta x delta y multiplied by 1, that is total volume, right? Now saying that, now we will for all the like derivation of Euler's equation or Bernoulli equation, what we will do, we'll do force balance. That means the summation of all the forces will be is equal to mass into acceleration, right? So if we do the summation of all forces, first what will come? The pressure force P delta y minus P on pressure on this side of fluid element. So this will be P plus del P del x delta y plus rho Bx delta x delta y. And this is delta rho into delta x delta y multiplied by del u. This is acceleration. This is the mass. This is acceleration.
Ma'am,
Yes, tell me.
ma'am, you are writing and explaining it, don't you? Because the screen is not visible.
It's not visible?
No. Just that NPTEL introduction page is visible.
Priyanka, is it visible to you?
Visible, visible for me, ma'am.
I think again the same problem, you have just turned on one screen. So I am teaching on both of them. On one, the question will be displayed, and on another, the writing pad will be visible.
Okay,
So
okay,
you have to
okay, ma'am.
take both of them so that
Yeah,
you can see the question as well as the answer. So now I am
okay, ma'am.
writing on the writing pad. So you have to tag that writing pad. Are you able to do that?
Can you help me, ma'am?
Yeah. So you can see on the participants, like at the down right section, the participant icon is there.
Yeah,
So you can open the
yeah, yeah. I
participants.
can see, ma'am.
So
Yeah, yeah.
yeah,
I
there
got
are
it.
two icons for me, rather three
Right.
icons. So one will be the for the PPT, another will be for the writing pad. So you tag both of them, like pin both of them on the main screen. So you will be able to see
Okay.
both of them. Is it fine?
Yeah, yeah.
Okay. Then. Okay. So simply the acceleration we have already studied in fluid kinematics. That is the temporal part and and uh, the bulk acceleration. That means the on the x-axis, on the y-axis, and the z-axis because of advection. Okay. So now after this, we'll just do the balance. So this will give us minus del p del x plus rho bx. This is the body force multiplied by density into del u del t plus q del u del x plus b del u del y plus w del u del z. So this is what we have learned about the Euler equation. So there will be just one second. So there will be one the pressure differential term, another will be the body force, and another will be the uh, basically this is the acceleration part where there will be temporal part and the advection part, right? So now this will help us to track the motion change along the x direction, this Euler equation. Now let's suppose if I give you an example like v is equal to ax I cap, that is the one velocity vector that I am giving to you, that is v is equal to ax I cap and ay j cap, and g, that is the acceleration due to gravity, is along negative z direction. Then find the difference between two pressure points, that is at x1 y1 and at x2 y2. This is point 1 and this is point 2. So a this area is sorry, this constant a is not a function of z. So this is the velocity vector that is given to you. So now as per Euler equation, by using the Euler equation, you need to find out the pressure, like the pressure gradient rather. So can you do that? I think sir have already given these examples in the class, so you'll be able to do that. So this is the velocity vector that is given to you. Can you do that?
Yes, ma'am.
Yeah, do that then. You need to get the expression for pressure. So P will be something plus some constant. So when you will be integrating it, it will be some constant. So this constant should not be a function of x, y, or z. Right. So this P is on the basis of x, y, and z. So what you need to do? First, you need to find out del P del x, then you need to find out del P del y, and then you need to find out del P del z. And you add all of them. Then like after integrating, you add all of them up and you will get one combined expression. So for like in case of del P del x, that will be the pressure equation that you get, that is a function of y and z obviously. And for y like del P del y, it will be a function of x and z. and for del p del z it will be a function of x and y as well. So when you club them clubbing them like or clubbing up all of them, the resultant constant that you are getting won't be a function of x y z or either way. So okay, so I won't be going into much detail. You find out this expression, then we'll discuss about the solution. I'll give you 2 minutes for this.
Oh, ma'am, could you please scroll up a little bit?
What? Pardon?
But could you please scroll up a little bit, ma'am,
Oh,
for
oh,
the
sure,
question?
sure, sure. Yes, yes, yes. This one. This is the equation. You just need to put the Euler equation, and in the Euler equation as oh, some details that I need to give you is that there is no temporal variation. That is, it is steady state fluid. So del U del T or del V del T or del W del T won't be there. Right. Next thing is there is no body force. Body force is only along z direction. So remember that. And another thing is just 1 second. Yeah. So we have velocity components only along x direction and y direction. There is no velocity component along z direction. So with this idea, we'll move forward.
E is not a function of z, ma'am.
A is not a function of z. Okay, we'll do. I'll come back in 1 minute. Hello, have you done? Have you solved it?
Yes, ma'am.
Okay, so what did you get?
Uh, P is equal to
Hmm.
minus rho a square by 2
Hmm.
into x square plus y square
X square plus y square. Okay. Into v
minus
square. So which one you are telling? The combined one?
P is equal to, ma'am, combined one,
Okay. Hmm.
minus rho gz plus constant.
Okay. Let me check once. Hmm. It should be actually rho of a square upon 2 multiplied by v square plus rho gz plus c constant. It should come about like rho a square x square upon 2 minus that is minus and minus rho square y square sorry rho a square y square upon 2.
Yes,
So
ma'am.
yes, so that a square I can separate, and that x square plus y square, that will be like simply that will be v. So that can be considered as v. So we can write it all together.
Yes, ma'am.
Okay. So mm, Brito, I don't know what's your name. So have you solved it, or are you facing any problem?
Uh, uh, no, I haven't.
Okay. See. First of all, we'll try it for x-axis. This is very simple. We'll just apply the Euler equation. So what does the Euler equation tell us? This is the Euler equation, this one. So we'll just apply this, and we'll check which one is like which of the component exist and which one doesn't. So first of all, if for x-axis we write del p del x plus rho of bx is equal to density, the temporal component, plus u del x, the acceleration part, plus v del u del y, plus w del u del z. Now, it is steady state, as I've already told you, so this will be 0. The body force is not there along x direction, so it's already said in the question. And this one, there is no variation of u along y direction, as we can see from the expression. There is no variation of u along y direction. So this is 0 and this is also 0. So only thing that remains is minus del p del x is equal to density multiplied by del u del x. And if we multiply del u, like if we differentiate del u del x from this equation, what will we get? We'll get density ax multiplied by a. So this is a square density into x. So del p del x is equal to minus a square rho of x. So this p is equal to minus rho of a square x square upon 2 plus some function of, like we are integrating it now, so it will be some function of yz. So similarly for y axis, if we will get, so that will be p is equal to minus rho a square y square upon 2 plus function, like if this is f1, this is f2 of function of xz, because this is in y direction. Now for z direction, similarly, like here we can see there is no component of velocity along z direction. So obviously that del w del x, that part will be like u del w del x, that part will be all like wholly omitted. So we will only have what? We will only have minus del p del z minus rho g, because here body force will be there. Body force is only along x direction. So if we will write this up like integrated, this will be minus rho g z plus function of some function of x. So now nothing, we'll just add this all up, and if we will add this all up, that means this is one equation. Let me use some other color. This is one equation, this is one equation, and this one equation. We'll just add up. Then all of this function will this function, and this function will altogether give one single constant that won't be dependent on either x, y or z. Simple. So we'll get pressure equation as density a square upon 2 v square plus rho gz plus some constant. Now, can you tell me what will be the rate of shear deformation? Previous week we have done the rate of shear deformation. How we'll find out? Can you find it out?
0, ma'am.
Yeah. And then rotation?
0, ma'am.
Yes. And then can you find out the equation of streamline? Prito, you tell me. Have you attended the session, previous session?
No, ma'am, I haven't attended.
Okay. So let me give you a,
I'm
have you taken the classes? Do you know what is
Yeah,
shear
classes I
deformation?
have taken.
Okay, then
Streamlined, it is a du by x equals to dv by x, dv by y, right?
dx upon u is equal to dy upon v.
Uh-huh.
And the rate of
Okay.
shear deformation is simply xy. You have already done that in the class, I guess.
Yeah,
So that is
yeah.
del u del y plus del v del x. So when we'll like u is only function of x, so this will be 0 and this will also be 0. So this is total 0. That means there is no elongation or stretching of the fluid element. Simple. Another is for rotation, we will find omega xy, that is half of del u del y minus del v del x. So this will also be 0. That means there is no rotation of the fluid element. So there is only like motion, the dynamic motion of the fluid element. There is no rotation, there is no elongation or stretching, like elongation or a contraction, anything. So now we need to find the equation of streamline. Can you find that out? Simple. Del x dx upon u is equal to dy upon v. Just put all the values here and you will get the equation. Have you solved it? Okay, I'll be waiting for 1 minute. If anyone of you solves it, then please unmute yourself and tell me answer.
X by y equal to k.
Xy is equal to k, correct. So simple. So this is dx upon ax is equal to dy upon minus ay. So if we'll integrate it, this will come out xy is equal to k. That means the rectangular hyperbola. That means the like profile will be like this. If this is y, this is x, this is the direction of motion. Okay, so let's proceed to the derivation of Bernoulli equation. So this will be done from like the derivation will be done from the Euler's equation. So like if I take 2 points and if I take a line element in between these 2 points, okay, sorry, just 1 second. If I take a line element between these 2 points, so this will be dl is equal to dxi cap plus dyj cap plus dz k cap. So if we find out dp, how to find out dp? That means the pressure gradient. So dp simply is del p del x dx plus del p del y dy plus del p del z dz. Please unmute yourself and ask me any question if you are like not understanding anything. So This del p del x we can write simply from the Euler's equation. Right here we have already written this one from this equation. The pressure gradient is equal to body force along with the advection terms, that is the mass into acceleration. So this we can write as minus density del u del t plus u del x plus v del u del y plus w del u del z plus density into bx. So this is written as the this whole equation. So this one, let me use some other color. So this one we can write as how, like in what form? This will be v del of u, right? This can be written as that. Now this, if we will write here, this will be dp is equal to minus density of del u del t plus v of del u dx. So this is just, we put this in this main equation. Similarly, del p del y also will put, and del p del z also will put. So this will also have the body term, body force term, and minus density of del v del t plus v vector dot product of del v dy dy. No, not here. Okay, sorry. This will be here dy. And okay. Okay, now this will be minus, this will be plus density of by. Similarly, we'll write up for z. I'm not going to much detail. So if we will multiply, if we'll separate the terms, right? We want to bring that this temporal terms together, right? And we want to separate these like advection terms together and this body force term together. If we will do that, then how we can write this up? This is density multiplied by del u del t dx plus del v del t dy plus del w del t dz minus density of v vector dot del u dx plus v vector del v dy plus v vector del w dz. So this is term 1, this is term 2, and another one that is left, that is the body force term, that will be bx dx plus by dy plus bz dz. So this is term 3. Simple. So if we write up the term 1 again, so term 1 means this part. So this part, if you will write, we can write this as density del v, like this vector, this we can write as this 3, we can write as v vector, right? So this will be del v vector del t multiplied by, this is the elemental vector, so this is dl vector. Now assume that the body force is only along z direction, and bx is equal to 0, by is equal to 0, only along z direction body force is there. So if we will write this like this part, that means v, this thing we can break down in vector form. So in vector notation, this is v dot del v vector is can be written as half of del v vector dot v vector minus v vector cross del cross v vector. Okay, so now the term 2, this the whole this big term can be written, can be shortened up. So this can be written as minus density, that means this is term 2. This term 2, the density v vector dot del v vector dot dl vector. So this is equal to minus density half of del v vector dot v vector minus v vector cross. Okay, this term can be written as zeta vector. That means this is vorticity vector. Vorticity vector. So here also we can write as zeta vector dot dl vector, that is line vector. So this can be just broken up as del rho half of this v squared. So this is I cap, del means del x, del x v square plus j cap del y v square plus k cap del z of v square. So these multiplied by this line vector. So how we can write that up? So this line vector means dx I cap plus dy j cap plus dz k cap plus this density multiplied by this one. So this can be written as v vector cross zeta vector multiplied by dl vector, the line vector. So this can be written as this whole thing. This whole thing again can be written as density into half of del x v square dx. So like we have just multiplied, like there is dot product, no, we have just multiplied both of them. There is dot product in between this part and this part. So we have just multiplied the combine the dot product rather. So if we will do that, this will be del x of v square dx plus del y of v square dy plus del z of v square dz. Okay, so this again plus density of v vector cross zeta vector dl vector. Now term 3, the last thing that is left is term 3. So as it is assume that there is no body force in x or y direction, only z direction, so this will be rho g dz. Other things will be getting cancelled out. Finally, if we will write the whole equation, this will be density del v vector del t dot del dl vector minus half of rho d v square this whole part plus density of dl vector dot v vector cos zeta vector this part so minus density g dz is equal to, sorry, this one is cross, right, cross. So this will be second. So this will be dp, the pressure differential. So this is dp plus half rho dv square plus rho g dz plus rho del v vector del t dot dl vector. So minus density into dl vector dot v vector dot zeta vector is equal to 0. Now this part can be 0 in many cases. This can be 0 when dl vector is along the streamline. That is the line vector is along the streamline. Then point 1, point 2 is when zeta dash is equal to 0. That means the flow is irrotational, right? And the third one is v vector dot zeta vector cross zeta vector is perpendicular to dl. If this is perpendicular dl, then their dot product, there is dot product, right? So then their dot product will be 0. So now we'll take examples, 3 case examples or case studies. So first one is, take a case along the just one sec, yeah, take a case along a streamline steady flow. So if we take a case along streamline along a streamline and steady flow. If this is the case, and we'll first write Euler equation of motion for streamline. So dp plus half rho dv square plus rho g dz is equal to 0. This is valid for only for incompressible, valid for both incompressible and compressible flows. So if we can write it as we just multiplied by density, so dp by rho half dv square plus rho, sorry, density of integration of g dz is equal to 0. This is 1 to 2, 1 to 2, 0.1 to 0.2. So if we will sum that up, then assume pressure is constant. If pressure is constant, this will just become P2 minus P1 upon density plus half of V2 square minus V1 square plus G Z2 minus Z1 is equal to 0. This is the Bernoulli's equation. And the Bernoulli's equation assumption that we have taken is inviscid flow, steady state flow, density is constant along a streamline. So Bernoulli's equation can also be written as P1 upon rho G plus half V1 square by G plus Z1 Z1. So this Z1 can be written as Z1 mg upon mg. That means the potential energy upon the wave. And this also can be written as half of mv1 square upon mg. That means the ratio of, the kinetic energy per unit weight. And this is the flow energy per unit weight or the flow work. Now, for second case, like this is the case 1 that we talked about. Second case or the example 2, we can write up as inviscid plus along a streamline. But it is unsteady. So if that is the case, then they again write the Euler equation plus half density of dv square plus rho g dz. Rho g dz is equal to, this term won't be cancelling out. This temporal term will be there, right? So if this term will be there, this will be density minus rho del v vector del t dot dl vector. So this is along a streamline. Along a streamline means ds vector, and this can be written as density into del v del t into ts. If this is the streamline and this is the the es vector, now if the direction of the streamline is given as this, then v vector can be written as v of zeta s vector. So ds vector is equal to zeta ds, zeta vector d, zeta cap ds. Right? Now if let us suppose pressure is constant, if pressure is constant, then this can be written as, if pressure is constant, this can be written as dp upon rho plus half of dv square plus g dz is equal to minus del v del t, temporal term ds. Now if we'll integrate it, 1 upon rho dp 1 to 2 integration plus half of dv square 1 to 2 plus 1 to 2 g dz. So this will be equal to minus 1 to 2 dv upon dt ds. Now if we will write this up, this will come out to be P2 minus P1 upon rho plus V2 square minus V1 square upon 2 plus G Z2 minus Z1 is equal to minus 1 to 2 dV by dt ds. So P1 upon rho plus V1 square upon 2 plus G Z1 is equal to P2 upon rho plus V2 square upon 2 plus G Z2 plus 1 to 2 dv del v del t ds. This is unsteady for unsteady case of Bernoulli equation. The flow is not steady. Now example 3, for example 3 we have, this is case 3. So for case 3 we have irrotational flow. That means points and z taken such that they need not to be along the same streamline. So we can write v vector as del of phi. So this we already know from the previous class. So this can be written as I cap del phi del x plus j cap del phi del y plus k cap del phi del z. So dl cap is equal to I cap dx plus j cap dy plus k cap dz. Now the term 1. Term 1 means, just one second. Yeah, this one. Term 1 means this one. That means v del v del t, so dot product of dl. So if we do that, del v vector del t dot product of dl vector. So del t of del phi del x dx plus del phi del y dy plus del phi del z dz. So this whole thing can be written as d phi, right? So this will be is equal to d of del phi del t. Now for Euler's equation will give us, dp upon rho plus half of d of del phi square plus g dz is equal to minus d del phi del t. This is for inviscid and irrotational flow. The factors making an irrotational flow to a rotational flow. Okay, so you give me your feedback. How can a irrotational flow become a rotational one? Anyone?
Ma'am,
Yes.
like according to sir, like he gave like some points, like how it will become rotational.
Yes. Can you tell
Uh,
me some?
if there is presence of any solid boundary
Hmm, hmm, hmm.
and Coriolis effect
And viscous effect
and viscous effect and shock waves.
and stratification. Thermal stratification means, let's suppose if there is an area, right? If there is an area where the temperature is high and an area where temperature is low, so where the fluid, when the fluid is passing through this both the region where the temperature is low, its density temperature is low, its density will be high. As we can see, density is a function of temperature, right? So where the temperature is high, the density will be low, and because of this there will be stratification, means there is a variation in temperature in both of the region. If there is a variation of temperature, there is a variation of density if there is a variation of density, then the flow may become like, if it is not like, even if it is not rotational, if it is in same direction also, it may become rotational, right? Understood?
Yes, ma'am.
Yeah. So I think sir have taught you that in class, no, where a plate is there and there is porous plate at bottom and fluid is entering from the bottom plate, and then we need to consider a control volume here, and this is b by 2, this is b by 2, and this is length a height h, and the length is l.
Yes,
So
ma'am. Solve this example.
yes, so we need to find out the weight of that plate. So yeah, if sir have done that in class, so we won't go to much detail of that. Okay. So Then sir have also done in the class the Euler equation for motion in streamline coordinate.
Yes, ma'am.
Okay. So actually based on this question, we will solve one question today in problem session. So where like in this, like let me give a like a 1 minute idea of how to solve this, so that you can solve the question that I'll be giving you today. So first of all, see, if we will find out the upthrust, that is the pressure that is applied on this plate, then it will give us an idea that what should be the weight of the plate to keep this plate in equilibrium, right? Because they should be equal and opposite. So if that is the case, then let's suppose V naught is the velocity of the initial fluid from the bottom, from initial fluid that is entering the bottom plate. And again in the previous week also we have done the same question, that the rate of flow that is entering is equal to rate of flow that is leaving. So if the rate of flow that is entering is V naught, is the initial velocity is already said into XL. This is this is X, right? This is X, the fluid element. Sorry, the control volume. So this is X multiplied by L is this distance, and if velocity we are considering the change of velocity along X direction, so that is Ux. So that will be like that is leaving the system. So this will be u function of x, the velocity that is leaving the system we do not know. So this will be ux multiplied by hl. H is this height. So now we got like in the class also you have seen, this will be v naught x upon h. Now, from the Euler equation, we know that del P del x is equal to density minus density of density into acceleration. So, if we will apply the continuity equation, a1 v1 is equal to density, this is 1, density 2 into a2 v2 bar. So, density will cut off when the flow is, well, this is valid obviously when the flow is steady. So, this ax will if we will write this is del u del x. So this will come out to be v naught square x upon h square. So simply we are putting this here. So if we are putting this here, this and del p del x will get us is equal to minus density v naught square x upon h square. So x is equal to 0 to x is equal to b by 2 and y is equal to h. So, pressure equation will find out as density into V naught square H square x square upon 2 plus C1, and at x is equal to B by 2, P is equal to P atmosphere. That means at the end of the plate, use some other color, at the end of the plate, that is at this point, at this point the pressure will be equal to the atmospheric pressure. So this we will be replacing. So we'll get P is equal to P atmosphere minus density V naught square H square x square by 2 plus density V naught square H square B square by 4 upon 2. So the net upthrust can be like, see, this pressure we have found out for only one side, only this side. So for both of side it will be twice. So simple. So it will be P is equal to so that will be equal to the weight of the plate. So this is twice of what we found out. So 0 to B by 2, P minus P atmosphere, this part P minus P atmosphere dx multiplied by L, because this is pressure we have just converted that into force. So this will be is equal to weight of the plate at equilibrium. So I think you have got an idea of how to solve this kind of question. So we'll just simply do like what is entering and what is leaving the system. So we'll take a control volume, we'll take what is entering and what is leaving the system. Then we'll simply apply the Euler equation in that case. Okay, so I won't go to the streamline part. So we'll directly move into the question now. Let me share today's first question. Okay. So a steady and two-dimensional inviscid flow field is represented by the stream function psi a x square y, where a is known as the dimensional constant. So there are 2 points given P and Q in the flow field. Which among the following statement is or are correct? If the flow field is irrotational and the flow field is rotational, or the Bernoulli's equation can be used to evaluate the pressure difference between the points P and Q, and Bernoulli equation cannot be used to evaluate the pressure difference between points P and Q. Which of the following statement is or are correct? So your stream function is given, and also the points, the 2 points in the flow field are given. So simply with the help of stream function, we can find out the velocity component u and v. And as we can find out the velocity component u and v, it's written the fluid like we should first check whether the fluid is rotational, because the in the options is given fluid is rotational or not. So we'll first check fluid is rotational or not. That means del cross v. So del cross v will check. And the next thing, like, see here is or are given, that means more than one option may be correct. So first of all, we'll check the rotationality, and the next thing is that Bernoulli equation can be applied or not. So we'll check whether, like, what are the assumptions that are given here, and whether what are the assumptions that we use in Bernoulli equation. So if that is the case, then it can be applied, or not, it can be found out simply. So you can solve this question, right?
B and C, ma'am.
Yeah. Pardon?
Answer, ma'am. B and C, second one and third one.
B and C. Just 1 second. B and another one is mm, yes. Yeah, correct. So can you tell me what equation did you get for the stream function rather?
Actually, I like here I did directly, ma'am. I used Laplacian. If it was not satisfying Laplacian, so it means that it is not irrotational.
Rotational is fine, but that is one point. Second, like C or D, which one is correct? You also have to check that.
That
So,
one for stream, like if it is along streamline, then stream function will be constant.
hmm,
So at points P and Q, I'm getting 9a, same constant stream function. So it is
hmm.
along a streamline. So we can
Not
apply
like that.
Bernoulli
You
equation.
have to check whether the stream function is valid or not. Like stream function is applicable or not. Whether you can derive the stream function or not. Like if stream function is valid, then point at point there are 2 points given, right? P and Q. So in both the, like, when you derive the stream function once, you will check that what is the value of stream function that is coming at with point P, that means with the coordinates that is given at point P, and with at point Q. So if P and Q are satisfying, both of them are satisfying stream function, then it's fine. That means the Bernoulli's equation is applied. Solve in that way. Okay.
Yes, ma'am, it is satisfying, ma'am.
So have you found out the equation of streamline?
No, ma'am, we have the stream function itself, no, ma'am.
Yeah, correct. But
So
but you have to check whether the flow is along the streamline or not.
along the streamline, stream function will be constant, no, ma'am.
Yeah, stream function will be constant.
So here, if I put like points, like coordinates,
That only, that only.
that
So in you can do in that way also, where you find out the stream function. The stream function will be constant along the streamline. So for both points P and Q, the stream function should be same. The value should be same rather. So in that way also you can do, right? So have you understood?
Yes, ma'am.
Yeah. Brito, have you solved it?
Yeah, I understood from that your explanation, ma'am. That xi when
You
we put the
solve
coordinates and the values of
you solve once by yourself. You can
okay,
give
ma'am.
1 or 2 minutes on this. You solve it, then I'll show you the solution box.
Okay, ma'am.
Okay. Okay, Priyanka, we should wait for him for a bit, 2 minutes, and then we'll proceed with the solution and then for the next question. Okay.
Yes, ma'am.
Okay, sure. I'll be back in 1 minute.
Yes, ma'am.
Okay, sorry for the delay. I got a call actually. Uh, so have you solved it, Brito?
Yes, ma'am. The flow field, it is a rotational flow field, so we cannot use the Bernoulli's equation to solve the problem. But the xi function, it shows that it is along the streamline.
So Bernoulli's equation is valid, right?
It's along. Bernoulli's equation is not valid for a rotational flow field, right?
But it's valid here. Like if it is along the stream function, see, it is inviscid flow, it is steady state flow. And another thing that we
Uh,
need to check is whether it is along the streamline or not. So
right.
three things are valid, then Bernoulli's equation is applied, whether it may be rotational or irrotational, doesn't matter.
Okay.
Okay, uh, so what are your options then?
B and C then.
Hmm. Whether the flow may be rotational or irrotational, Bernoulli's equation is bound to valid. Like with Bernoulli's equation, like see, if like a fluid is also flowing in between a pipe, and we are applying like we are connecting a manometer, we'll solve these equations later on. So we'll be applying the Bernoulli's equation over there. Like what is the total energy here at point 1 and what is the total energy at point 2? Bernoulli's equation will only be applied there. It doesn't matter whether the flow is rotational or irrotational. The microscopic things doesn't matter. Here the we'll check the dynamics, the macroscopic thing, right? So whether the flow may be rotational or irrotational, this three things that we need to take into account is that, because see, the Bernoulli's equation, from where does it come? From the Euler's equation, right?
Yes.
So if we check on the Euler's equation, did it go? Yeah. So from this Euler's equation, we took some assumptions, right? So this term 1, term 2 and term 3. So in that we took that the flow is steady. That's why this term, this del t term, where did it go? Just one second. This term we are just cancelling out in Bernoulli's equation, right? This term we are not using because we are considering the flow is steady. We are assuming that
Hmm.
rather. And also we are considering that the flow is like inviscid flow. So that's why density also we are considering constant. And also we have to check whether the flow is along a streamline or not. So if the flow is along a streamline, then we can say that okay, the Bernoulli's
Bernoulli's
equation will
equation
be
can be
valid.
applied. Okay.
Yes. So
Okay. Okay. Yeah.
when like in this type of question is given, like later on you will see in the next week. Like I don't know what sir have taught in the this week because I have not attended the classes yet. But this kind of problem will come, this manometric problem. So this manometer problem, if it is said that like this is some level, like this there is mercury, and this mercury like here pressure will be more, and here pressure will be less, sorry, this will be up. So here pressure will be more and here pressure will be less. That's why, because of this pressure difference from high pressure to low pressure, the fluid will be moving, right? So over there only, like as we can see, this manometer is horizontal. So what does it come? P upon rho g plus v square upon 2g plus rho z, right? Rho gz. So this is equal to constant. So this term will be cancelling out because this is horizontal, and only the velocity term, like this velocity term. And since here the velocity is also will be constant, because here as we can see the volumetric flow rate is constant. See, the area at point 1 and point 2 both are same, right? The area is same, right? Area is
Yes.
not changing. So
Yeah.
as
Yeah.
the area is not changing, well, volumetric flow rate means what? Area into velocity. So as area is also constant, volumetric flow rate is also constant, velocity is also constant in this point. So this will be won't be varying in between point 1 and point 2. So only the pressure will be varying in between point 1 and point 2. So only the pressure will be varying. So that's why we can see that from high pressure to low pressure, this from high pressure to low pressure, the fluid is moving. So here we are applying the Bernoulli's equation. So it doesn't matter whether the flow is rotational or irrotational, the Bernoulli's equation can be applied anywhere. So yeah, now um, first of all, like as Priyanka has already done, so and also Brito has also done. So first of all, we'll check the rotationality of the flow. So ijk, so simple, del x del x. We have also done this in the previous week, right? So del z u v w. So this is del v del x minus del u del y. So this is minus 2ay. That means this is not equal to 0. That means the flow is rotational. Another thing is that we need to check the stream function, like stream equation, whether it is valid or not. So we'll find out first the stream equation. So stream equation is del x upon u is equal to del y upon v. So u means ax square and v means 2 minus 2axy. So dx upon x is equal to dy upon minus 2y. So if we will solve this, we'll get x root y integrate after integrating is equal to constant. So at both of the point P and Q, we'll find out the value. So at point P, x1 is equal to 1 and y1 is equal to 9. So root 9. And at point Q, we'll check again. So this is x is at point Q is 3 and y is root 1. So that means what? This is also 3, this is also 3. That means at both of the point, the stream function is stream function values are equal. That means it is satisfying at both of the point, the stream function is satisfying. That means the equation, like the flow is following the Bernoulli equation. Like a Bernoulli equation can be applied as it is along the flow is along the streamline. Okay, let's proceed to the next question then. So as I've said, like this is the extension of the problem that we already did in the class. So here a heated rectangular electronic chip is floating on top of a thin layer of air above a bottom plate as shown in the figure. Air is blown at a uniform velocity v0 through the holes in the bottom plates as we have seen in the previous problem. Width of the chip perpendicular to the plane of the figure is L. Assume a steady, inviscid and constant density flow in the gap between the chip and the bottom plate. So first question in this is that velocity field in the gap between the so the velocity field in the gap between the chip and the bottom is given by which of the following? Simple. We have taken this control volume, and again in this control volume, we'll check the fluid entering and the fluid leaving. So with that, we can find out the velocity fields in the x direction and y direction. So can you solve that in the similar fashion only what we have already did in the class? You can solve this, right?
Doing now.
Yeah, yeah, sure.
Option D, ma'am.
Option
Last option.
D. Okay, fine. I won't tell you which one is the answer. Let Brito solve first. Can you tell me which one is the answer? Have you solved it?
Uh, um, Ma'am, I am not able to solve this.
It is very easy. Like you just apply the continuity equation, no? Conjugate equation, you know, right?
Yeah.
So here, what is the fluid entering and what is leaving? That will be equal. So fluid entering, I've already solved it previously in this class only, right? So density into area into velocity of the fluid that is entering and the fluid that is leaving, that will be equal. The total mass will be conserved. So from there, the if we take that the initial velocity is v naught, so v naught xl is equal to like x in is uh, the distance in rather the control volume in the x direction, and L, let's suppose it is in z direction. And for the leaving fluid is it will be velocity we don't know, so let us consider it ux, and h is the distance between the two plates, and L. So from there ux you will get, and also we know that del u del x plus del v del y is equal to 0. From there you will get v if we will integrate it. So obviously from that you are getting both of the equations. So can you solve it now?
Mm.
You understood, right? How to solve?
Uh, yeah, using the continuity equation, I have to proceed it out
Simple,
and
like when the
equate it
control
for
volume,
entry.
yeah,
Mhm.
what the fluid is entering and what is leaving, that control volume in from that control volume that will be constant. Do that. I am here only. I'll give you 2 minutes and then we'll proceed with the solution. Okay, I think we should proceed with the solution now because we have more problems to solve. Okay, so have you solved it, Brito?
No, ma'am. You just go ahead, ma'am. I'll just
Your voice is breaking. Okay, not a problem. I'll solve this. So question number 2. So first of all, what the fluid like as I've already explained in the derivation. So the whatever fluid that is entering, the mass of that fluid will be what is the mass of the fluid that is leaving. So this is if we consider v naught is the initial velocity of the fluid that is entering multiplied by xl is equal to ux, that is the velocity that is leaving, hl. So this is ux is equal to v naught x upon h. Now, hmm, so now del u del x, as per continuity equation we know that del v del y is equal to 0. So del v del y is equal to minus del u, just 1 second, minus del u del x. So minus del u del x minus v naught upon h. So So if we'll get v, if we'll integrate, we'll get v from here, that is v naught y h plus c. So boundary condition is at v at h is equal to 0. Obviously, when we'll move to the height h, due to the no slip boundary condition, velocity will be 0. So if we'll apply this will be 0 is equal to v naught h upon h plus c. So c is equal to v naught. So simply velocity y is equal to v naught 1 minus y by h. So answer is option D. Okay. So let's proceed to the next question now. This is the related question. So what we need to find? We need to find the acceleration of the fluid particle in the gap between the chip and the bottom plate. And the next question is the weight of the chip that can be. So that's why I have derived that weight of the chip part, like how we can find the weight of the top plate in order to be in equilibrium. So the weight of the chip again it's is asked here. So can we solve this? First of all, we know the velocity, so we can easily find the acceleration. And also the way we derived in the class, the same way we'll find the weight of the chip. So you can solve it out, right? Anyone? Priyanka, Brito?
Okay,
First,
ma'am.
Yeah. Solve it. I'll give you 1 minute for this. Okay, so have you solved it?
for the above question, option C, ma'am.
Option C. Okay, let me check. Yeah, first
Yes,
one is
ma'am.
option
Option
C.
C it is.
Then next one, weight of the chip.
Doing, ma'am.
Yeah, sure. Okay, you solve it. I'll be back. Have you done?
Second option, ma'am.
1 second. Yeah, correct. So let's solve this. I'll just give you, as you have already solved, so I'll just give you a brief of this. So acceleration, we already know that del u del t plus u del u del x plus v del u del y. So this will be is equal to v naught x upon h, v naught upon h. So this is v naught square x upon h square. So ay will be is equal to del v del t. So plus del u del v del x plus v del v del y. Similarly, so this will be minus v naught h 1 minus y by h. So this is option C. So next is the weight of the chip. So we'll obviously find out the pressure gradient. So as we have already done in the classes. So this the pressure gradient, if we will find out, so that will come out to be, just 1 second, minus rho v naught square x upon h square. So from like we will integrate from 0 to b by 2. So we'll get pressure is equal to, first we will integrate, so v naught square h square x square by 2 plus c. So at x is equal to b by 2, p is equal to p atmosphere. So p atmosphere is equal to density v naught square upon h square, b square by 4 upon 2 plus c. So c we will get from is equal to p atmosphere plus density v naught square h, b square by 4 upon 2. So we'll get p is equal to simple. We'll just put it here. So we'll get some expression for p, and the net upthrust will be twice of 0 to b by 2. This pressure, the pressure what we got into multiplied by area. So pressure multiplied by area will give what? Force. So total force that will be applied on the upward direction will be equal to the weight of the plate to keep in equilibrium. So this will come out as L rho v naught square upon 12 h square bq. So this is option B. Okay, so I'll proceed to the next question. So a tornado may be modeled as a combination of vortices with Vr and Vz is given as 0, V theta is given as V theta r, such that V theta is given as omega r for r less than, that is the inner region, r less than capital R. And when r is greater than capital R, the expression changes to V theta to omega r square upon capital R square upon smaller. Assume the flow to be inviscid and the fluid density to be constant. Also neglect the effect of body force due to gravity. Also assume that P is equal to, P tends to P infinity and R tends to infinity. Which among the following statement about this flow field is true? So can you solve this for me? So what is the flow field, whether the flow field is irrotational in the inner region or outer region, or rotational in inner outer, or vice versa? Can you solve this? Hello?
Doing, ma'am.
Yeah, sure. Do that. we solved it? Priyanka? Prito?
Just a minute, ma'am.
Yeah. So first we have to check the flow is irrotational or rotational. So for that, obviously IJK. So del del R, del del theta, del del phi. So we are v theta, v phi. So if we will solve this, we'll find that for r less than capital R, this will be 2 omega, and for r greater than equal to capital R, this will be 0. That means the inner side, that is the inner part, if the flow is rotational, and the outer part flow is irrotational. So have we got this answer?
Yes, ma'am.
Yeah. So that's correct. Then we need to
Mm.
find out the pressure in the inner region, and for that, first of all, we need to find out the pressure in the outer region. Then we'll solve for the inner region. And obviously there won't be any discontinuity, right? It will be gradually changing. So at point like at small r is equal to capital R, that means at the verge in between the inner and outer layer, the pressure will be same. So we'll just equate both of them. So have we solved it?
Pressure. Your pressure is not asked, ma'am.
Pressure is
Not asked. Only to find rotational and irrotational, ma'am.
pressure is also there, no?
Question in the question only which are the following statement is
Oh,
true.
okay, I don't know, like in the next question maybe then. Yeah, the pressure in the inner region.
Oh, okay.
Okay, I'm here only, you solve this. Just 1 second, okay. Okay.
Uh, Ma'am,
Hmm?
option A.
Let me check. It will be P is equal to P infinity half of 2 omega square r to the power 4. Omega square r to the power 4. Most probably it is option minus. It is option C. Hello? It's option C.
Okay.
Check once. I like for outer plane, like for outer region, it will be the P infinity minus rho of omega square capital R to the power 4 upon 2 R to the power 4. And if you are applying at smaller is equal to capital R, it will be the first option. But it is for outer plane, not for the inner region. For inner region, it will be like the velocity gradient will be changing. No, the velocity will be omega r. V theta will be omega r. So we'll be applying that. You understood, right?
For inner region, we are finding the pressure, ma'am. For inner region,
For
we are
inner
finding one
region,
pressure, and for outer region, we are finding pressure.
so for outer region, you are finding some pressure. So
Yes,
for
ma'am.
inner region also, you will get some pressure. So for
Yes,
inner
ma'am.
region and outer region, at the verge of these two, that is at smaller is equal to capital R, both of them will be equal, right? Let's suppose at at let's suppose at small r is equal to capital R. Hello. Let's suppose at small r is equal to capital R.
Yes, yes,
Let's suppose at small r is equal to capital R, P is equal to P naught. Let's suppose any some random value. So you will for the inner part, you will get some equation of pressure with some constant, right? So you need to find out that constant. So let's suppose you are putting at small r is equal to capital R, P is equal to P naught. So now we need to find out what? We need to find out that constant value. Let's suppose that constant is C2. So in equation 1, like for the first, that is the for the outer plane also, we'll put at small r is equal to capital R, P is equal to P naught. And then we'll equate both of the pressures. Because both of the pressure will be same at point small r is equal to capital R, right? So from that we'll get that constant, and we'll put the that constant value in that equation, the inner plane equation. So we'll get the equation then. You understood, right? What I want to say.
yes, ma'am.
The pressure can't be discontinuous, right? So whatever is the pressure at region 1, and when that means the inner part, inner region, and whatever pressure will at the outer region, there will be a gradual change. That means at point small r is equal to capital R, maybe before and after that the gradients are different, at that point the pressure will be same. So we'll use that concept only. Understood? Can I solve that now?
Yes, ma'am. Similar to what you told, I did, ma'am. Like for inner region, I got like P is equal to rho omega square R square by 2 plus constant.
Mm-hmm. Then
Then again, I did for outer region. Outer region also I got P. Sorry,
let's
P is
suppose
equal to minus.
let's suppose that smaller is equal to capital R, we are giving some value P naught to the pressure, right? So we'll put that boundary condition to both of the equation, inner and outer region equation, and then equate both of them. Then it will be easier for us because there will be only one variable, that is the constant. So that variable we can easily find out, right?
Okay, ma'am. 1 minute, ma'am.
Yeah, yeah, sure.
Could you solve it, ma'am? I think I'm getting stuck somewhere.
Okay, sure, sure, not a problem. Okay, so we need to find the pressure in the outer region first. So for the pressure in the outer region, del P del R is equal to rho, like this is just the Euler equation we are applying, right? So by Euler equation, we know del P del R is equal to rho V theta square upon R. And V theta for the outer region is given as omega R square by smaller, capital R square by smaller for R greater than is equal to R. Now, what we'll do, del P del R, we'll just put this in this equation. So it will be rho omega square R to the power 4 R cube. So if we'll integrate it, we'll put the we'll integrate it first. Let's suppose we'll integrate it rho omega square R to the power 4 to small r square plus constant, some constant. Now at r tends to infinity, p tends to p infinity, right? So when r is infinite, p will be p infinite. So if we will put this up, right? So it's already given here at p tends to p infinity, r tends to sorry, at r tends to infinity, p is equal to p infinity. So we are using this boundary condition only. So we are applying this. If you will be applying this, then p infinity will come out to be c1. So we'll put the c1 here. So we'll get p is equal to p infinity minus rho omega square r to the power 4 by 2 r square. So this is for the pressure field for the outer region. Now we have to find for the inner region. So for the inner region, del P del R is equal to rho V theta square by R again. Now V theta in this case is equal to omega R. Omega R. So P will come out to be rho omega square R square upon 2 plus C2. So at now as I said you, like the pressure gradient is like this, no? So there may be the gradient may change at this, but at small r is equal to capital R, the pressure is bound to be equal at both of the direction, right? Whatever equation we may apply, the pressure at one point will be equal. So let's suppose at pressure this point we are thinking the pressure to be P naught. So we are just applying this at small r is equal to capital R, P is equal to P naught. So if we are applying this, then P naught is equal to rho omega square R square by 2 plus C2. Now the pressure field should be continuous and not discontinuous, as I have already said to you. So this is one equation. Another equation will be this one. We are applying what? We are applying at small r is equal to capital R, P is equal to P naught here. You are understanding, right,
Uh,
this equation?
Ma'am, for second equation it would be minus rho
Yes.
omega square r square.
Which one?
Second equation. Yeah,
Which
that
one?
one.
Hmm.
Minus no, ma'am.
Minus y.
Dou p minus dou p by dou y.
Mm, okay. This is del p by del r rho v theta square upon r. No, this is the there is no minus, right?
No, no, minus del p by del r is equal to rho v theta square by r.
Is it?
In the top code, you wrote the same thing, no, ma'am.
Yeah, I wrote the
Top.
same thing. I have not taken minus. Check.
Oh, okay, 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 okay. Okay, it is integration. Okay, sorry.
Okay. So if we will write this, then what we will do? As small r is equal to capital R, we will write in this. In this equation also we'll write the same thing. If we will write the same thing, what we will get? We will get that P naught is equal to P infinity minus rho omega square R square upon 2. Let's suppose this is equation number 2. Let's suppose this is equation number 1. Now what? Both of these equation will be same because both of these are P naught, right? So P naught will be equating. So if you will be equating P naught, then this will be rho omega square R square by 2 plus C2 is equal to P infinity minus rho omega square R square by 2. So C2 will come out to be P infinity minus rho omega square R square. So this we will put in the main equation in this equation, right? So if we will put this in the main, not this equation, sorry, in this equation. So this will be P will be is equal to P infinity plus rho omega square by 2 R square minus 2 capital R square. So this is the main equation, that is the pressure field in the inner region. Understood? Any doubt?
No, no.
So it's very simple. So this kind of problem you can easily solve now. So can you tell me the lowest pressure in the flow field? Where is the lowest pressure and what is the lowest pressure? It's very easy, right? We just need to differentiate. Can you solve this?
Doing, ma'am.
Yeah, sure.
First option, ma'am.
Okay. Hmm, correct. So this is nothing but what we will do. We'll just put del P del R is equal to 0. Simple. So we'll get option A. Okay. Now let's proceed to the next question. An incompressible frictionless flow field is given as this equation, where A value is also given, B value is also given, and the fluid is water and G is given as Gj. Determine the x component of the pressure gradient at x y 2 2. So what will be the x component? So it's very easy. You can solve it. Just 1 second.
Minus 16,000.
16,000. Just 1 second. It will be minus 16,000. Check once.
Yes, ma'am. Minus 16,000.
Okay. So let's proceed to the next question. I think it's not required for this to solve, right? So you have solved it already. And it's very easy question. So we'll just use Euler equation here. There is no body force term and no temporal term, and del u del z will also be 0. So only del p del x is equal to minus rho of u del u del x plus v del u del y. So u is given and v is also given, and from there we can easily calculate, sorry, u is given, and del u del x we can find, del u del y also we can find. So we can easily find out del p del x from there. Any doubt? Brito, you have any problem in this question? Any doubt?
No, ma'am.
No. Okay, let's proceed to the next question then. It's already 9:06, sorry, 10:06 rather. So let's make it fast. Which of the following is not correct? It will take 1 second. Tell me. Not correct. Tell me.
Oh, B, ma'am.
Yes. Okay.
B, ma'am.
Yeah, correct. So, okay, this is question number 6. So, water is flowing through this nozzle, right? First of all, it is passing through the pipe, and then it is flowing through the nozzle. So, the diameter of the pipe is 2.5 centimeter, and nozzle is 1 centimeter. Obviously, the velocity will be increasing at nozzle. So, at nozzle, the velocity is 9 meter per second. Determine the minimum gauge pressure required at section 1 to produce a velocity at the nozzle 9 meter per second. You can solve it, right?
Doing, ma'am.
Yeah, sure.
588. Option C, ma'am.
Mm, option C. No. Check once again.
Sorry, ma'am. Option B, ma'am. 68893.
Yes, correct. So there is nothing, it's very easy question. So just P1 upon rho plus, just you will apply Bernoulli equation. So the height difference, the Z2 will be there, 3 meter. Then Z1 is 0. Velocity at 2 will be 9 meter per second. Velocity at 1, how we can find out? We can simply apply the A1 V1 is equal to A2 V2. That's volumetric flow rate will be same. So from there, V2 we can find out. So once we find out V2, then we can put in the main equation V1, sorry, we can find out V1. V2 is already given. So V2 we know, V1 we know, then Z2, Z1 to 0 only. Z2 we know, so P1 minus, sorry, P2 will be P atmosphere. That is, it is opening at atmosphere, right? So P1 minus P atmosphere upon rho also we know as 1000. So P1 minus P atmosphere we can find out. So that will be option B. Okay, so what is the pressure gradient normal to the streamline for a steady flow in a region where streamlines are straight in a horizontally? You don't need to think on this. It is very
0.
easy. Yeah, correct. Because 1 upon rho del P del N is equal, del R is equal to V square by R. As R tends to infinity, this thing becomes 0. That means pressure becomes constant. Simple. So let us proceed to the next question. There is like time has already passed a lot, so yeah, let's make this the last question, and we have 4 more questions. Okay, I'll give you those questions as homework, and we'll discuss that in the next class. So if you are facing any problem, then so can you solve this?
We'll try, ma'am.
Yeah, solve. So there are two circular plates that are separated by a liquid layer. The lower plate is stationary and the upper plate is moving downward with a constant speed. The radius of the top plate is capital R, and the distance between them is B. And the liquid is squeezed out in the transverse direction, that is in the sideways direction. The flow is invisible. What is the speed of the liquid that is coming out of the gap between the plates in the radial direction? Very simple.
C.
Option C. Yeah, correct. It's very easy. Like the fluid that is, if we will be applying conservation of mass, the fluid that is being forced by the downward movement will be the mass of the fluid that is coming out in the transverse direction. So that is pi r square v is equal to 2 pi r. Like it is considered, if we consider this a cylinder, so the fluid that is passing passing in this direction will be equal to the fluid that is moving out in this direction. Similar fashion what we did in the earlier problem. So bvr, so here VR is equal to V into multiplied by R upon 2V. So this is option C. Now, so what about the next question? What is the variational
A.
velocity? Yeah, A. So this is very easy. Del VR upon del T is equal to minus VR upon 2B square dB upon dt. So dB upon dt is equal to minus V. So del VR upon del T is equal to V square R upon 2B square. What about the next question? Variation of pressure in radial direction. Remember, we will apply Bernoulli's unsteady state Bernoulli equation here. So the unsteady state term will also be coming here. Have you solved it? Very easy, right?
1 minute, ma'am.
You just have to apply the unsteady Bernoulli equation. So this is P1 upon rho plus V1 square upon 2 plus GZ1 is equal to P2 upon rho plus V2 square upon 2 plus GZ2 plus 1 to 2 del VR by del T ds. So we'll be using this equation, and we'll take the 2 points on the same horizontal streamline, and there'll be no difference in height. So what we will do, we'll put the values for V1 and V2, right? So if we'll put the values for V1 and V2, then P minus, tell me.
Option B, ma'am.
Correct. So if we'll put this, we will P minus P atmosphere upon rho V square upon 8B square capital R square minus small r square plus V square by 4B square capital R square minus small r square. Simple. So this is option B. So this is the next question. You take down, like note down the next 3 questions. You can take a photo of this and solve it back at your home. I'll discuss the solution in the next week. Okay. Have you taken the photo of this image? A screenshot, anything?
Yes, ma'am.
Yeah. This one. Brito, you're taking the screenshot, right? Hello, Brito.
Yes, ma'am, I'm taking it.
Yeah, take the screenshot of this and solve it at your home. If you are facing any problem, you can tell me in the next week. So next week, not next week, actually this week only, we are having on the regular class on Friday, right? So at that time we'll discuss. So yeah, then there's the next question. This is the last question. So here we can clearly see that the cross sectional area is changing, right? So the pressure variation is there. And also as the cross section is changing, the velocity variation will also be there. The velocity head will be there, but horizontal, like potential head will, like potential won't be there. That means the gravity GZ, the GZ part, that won't be there. Only the pressure gradient will be there and the velocity gradient will be there if we will be applying the Bernoulli's equation. Okay, so you've taken the photos of all or the screenshot, anything you like?
Yes, ma'am.
Yeah, sure. Then I'll meet you guys next week. Not next week, this week on Friday.
Yes, ma'am.
And you solve this back at your home, and if you'll be facing any doubt, any issues, then do tell me. Okay.
Yes, ma'am.
Okay, meet you guys on Friday. Bye.
Thank you, ma'am.
Welcome. Bye bye.
Yeah. Bye, ma'am.